Finn, who's going to talk to us about conformal field theory, dual of general black holes. Thank you.
Thank you, David, and thanks for all the people who came, even though the talk was not advertised with a title. Is this on, or? It's on, okay. Just as you can see, what I'm putting on here is sort of a long-term program. I'm going to not spend a lot of time on technical details and long computations. Instead, I'm going to try to outline a vision for where I think we should be heading with black hole microstate counting. Well, we're not there, and there'll be a lot of questions, and I think this works for this kind of workshop setting. So I'll start with this big picture, and it's really going to be very, very simple. I'm going to do a time-honored analysis called phenomenology, answer analysis, and that way we'll always get the right answer. And based on that, I'll sort of read into tea leaves where we're heading, and the two actual results that I have that are sort of newish is one way of organizing black hole thermodynamics, which is a bit different from the way it's normally done, and it seems to be mysteriously powerful, so I'd like to present that a little bit, and then I'll talk about the program of trying to discover conformal symmetry for black holes, even when there isn't evidently anything, but trying to look at the near horizon geometry and somehow squint your eyes and see, well, maybe there is a conformal symmetry after all. This is both very ancient stuff from the late 90s and two papers that are relatively recent, and it's also related to the paper by Castro, Maloney, and Strominger from a couple of years back. So my guiding assumption has been for a long time, that the very general black holes, very general means that we are in some theory that n bigger than 2 SUSY or so, and when you look at the general black holes of those theories, it seems to me that there are signs that there should be a dual 2D CFT description. This is not an ADS statement. This is just, well, due to evidence that I like to share with you. Now, the guiding assumption is very, very strong. What I have in mind when I say general black holes is that this should work for Kerr black holes, it should work for Schwarzschild black holes, it should work, of course, for all the string theory black holes that have some nice limits, that have ADSs and that have supersymmetric limits. But I have in mind that we should be in settings that are such that we have all these different limits available to us. Because I think that there are different, by having all these limits available to us, we see the structure better than going any one limit. Yeah?
These are asymptotically flat black holes.
I have in mind asymptotically flat, yes.
Because, I mean, for ADS, we know that the dual CFT should be n equals 1.
This is fair. Yeah, that's right. I have in mind asymptotically flat. Very good. Now, although I'm very ambitious, I'll be ambitious mostly in one direction. I will have in mind that it's okay, for now at least, if we could discover a very precise version of semi-classical conformal symmetry, I'd be very happy. So it's okay for me for now to look at large black holes and to restrict to just the asymptotic behavior of the entropy. And that limit might be enough to specify things like the conformal field theory central charge, at least in the large central charge limit, and its temperature, and try to somehow account for the black hole entropy in the semi-classical approximation. That's what I would consider success at this point. But I should mention, even though for that there really is not that much evidence, that I'm still hoping that somehow there's a precise counting of black hole microstates for every black hole, including the Schwarzschild and Kerr and these non-supersymmetric examples. And the way one should work with that is that somehow there should be two chiral sectors, each are represented by SUSY states, but that basically there are two chiral sectors and we should put them together at the non-perturbative level in much the way we normally do for perturbative strings. Some kind of direct product would certainly give the right result, and what we need to figure out is what the details are. And I think the kind of semi-classical reasoning that I'll show sort of points us the way towards such a long-term goal. So let me start with the phenomenology and start with just the simplest things, those that are no fancy stringy stuff, the entropy of Kerr black holes. The analysis I have in mind when I say phenomenology and answer analysis is that it's very suggestive that this entropy formula clearly comes in two terms. There's this term and there's that term, and it's an addition of two terms. And the way to think about it, I think, is that the first is part of a chiral half of the conformal field theory, and the second is due to another half of the conformal field theory. And in the semi-classical limit, these entropies from the left movers and the right movers should just be added together in the simple way. So that is the phenomenological starting point. If one buys that starting point, one buys something, one gets something, one says, okay, now I know a little bit more than usual. I know not just what the entropy is, I know what the entropy is of my left movers and right movers separately, and I know how they carry energy, because I know how these things depend on energy, so I can find not just a usual temperature by using the first law of thermodynamics. I can use the first law of thermodynamics separately for my left movers and for my right movers. Of course, I'll get the standard Hawking temperature if I do it for the sum, but that's not what I have in mind. I have in mind that we have inverse potentials for right movers and left movers separately. And this is then an important part of the sort of phenomenological analysis, that if you think that there really is, in whatever framework you have, that somehow this is left movers, this is right movers, you have separate temperatures.
What's the intuition for that script?
I mean, come on.
With the small j, large mass, it would just
No.
expand and it wouldn't look anything like that.
It will. But look, I'm trying to give you the picture, okay? So, now within this phenomenological model, this is, answer analysis, as I said, it's a phenomenological model. You do immediately get a model for angular momentum, because the angular momentum was entering these two left and right entropies in a very suggestive way, just as a minus j squared on the right side. This you can model if you think that your 2D CFT, that's dual to the 4D black holes, if only the right movers had the ability to carry angular momentum, and the left movers don't have the ability. For example, if the CFT was a 0,4 CFT, if we put our charge on the right side, but not on the left side, and so model the right side as being a supersymmetric theory with an SU2R symmetry, then that would account for the angular momentum dependence entirely. And this would then be the kind of model that then automatically would get to the correct supersymmetric extremal limits. So that gives some promise for how one can understand the functional dependence on parameters. I will stay to 4 dimensions, but if I were to go to 5 dimensions, which certainly we have in the papers, there'd be 2 angular momenta, and I would have in mind that you should use some kind of 4,4 superconformal field theory of the kind that has been analyzed a lot in the supersymmetric limit. We understand this indices very well, but I have in mind that you should try to understand the entire CFT. So, if you follow the suggestions that I make for the model, what I have in mind is that the general black hole, the Kerr black hole here, it should be basically understood as an entropy of a one-dimensional gas on a circle with radius r. And then the right entropy and the left entropy should both be written as just a standard one-dimensional formula. Entropy is proportional to the temperature, and we analyze now a free one-dimensional gas, simple as that. If you get this and you believe that indeed I was right in finding my right entropy and my left entropy and my right temperature and my left temperature, then you can from this formula here deduce what the central charge is. Not quite the central charge, but times central charge density, the central charge times the size of the circle is what you can deduce from this phenomenological model. And you find is that the central charge is given by some cubic formula in the mass. This should be reminiscent of the cubic formula that's well known for the MSW type black holes that are understood in terms of branes wrapped in a cubic kind of way. But here it's entirely non-supersymmetric in the phenomenological model. There is an encouraging feature at this point that should be noted, that once I had a right temperature and a left temperature, and a right entropy and a left entropy, I could compute the central charge on the right side and on the left side. And I could do that independently. And I find in this phenomenological analysis the same central charge on the right side as I do on the left side. This is not obvious. I'm not aware of any GR argument or any other physics arguments that I'm aware of at all that would ensure that. However, if I'm right that there is a dual CFT, then I would say, oh yes, because you see that dual CFT would have a diffeomorphism anomaly if the central charge on the left and the central charge on the right were not the same. And although that is okay in the quantum corrected theory, I would say in the semi-classical theory, I would surely not expect a diffeomorphism anomaly. So I'll take that as evidence that I'm on the right track. Weak evidence, definitely not compelling evidence, but still, it was not obvious that if one follows the phenomenological model, that one should actually get, you know, the same central charge, the same number of degrees of freedom on the right side and the left side.
So why are you going to say?
The ratio of my left temperature and my right temperature and versus their respective entropies is the same in the two cases. And this was not obvious. It has to do with the way the mass was entering in the entropy formula. All right, so I'm saying that the left entropy divided by the left temperature, S over T, is the same as on the right and left side. This is something you expect if there's a semi-classical CFT, but it's not obvious from other thermodynamic reasons. In general, why should S over T for these two sides be the same? But if there's a CFT, sure, that's what you expect.
I mean, if this is in some canonical ensemble, don't
Yes.
I put it in a bath and then then both sides will take the same temperature because it's just...
No. Well, I mean, it's, well, look, we obviously know that in the, yeah, look, no, these are not the same temperatures, right? These are, they're really, well, look, there's always a chemical potential for, you know, that can split left and right, and that gives you sort of independent temperatures. Maybe I shouldn't call them temperatures, but temperatures seem to be a good terminology because it, you know, anyway.
Just a comment, but the spectrum for the curve, I mean, it's not thermal, is it? So the fact you have two different temperatures could explain, that's a good feature, they have two different ones. Does that suggest that means...
What do you mean it's not thermal?
Well, what I mean is we have different temperatures, there's an instability. And you know there is
Yeah.
an instability in the curve, it
There is.
spins down.
The superradiance, you mean, superradiance
Superradiance.
stability, yes. That is a feature that, yeah, that, look, it fits into these thoughts, but that has been relatively well understood in the Kerr CFT sort of story near extremality, where one can indeed understand the superradiance stability. So this would be guessing, yeah, that yes, that picture would fit also far off, but there, you know, I can give a lot fewer details. Yeah. So the other thing that I want to focus on, that I want to emphasize because it's important, is that in CFTs, we normally work with dimensionless temperatures. But here I've identified, using the first law of thermodynamics, a dimension-full temperature, the physical temperature. So these ones here I do not negotiate. I know for sure in advance what they are, but I might negotiate what the CFT temperature is at this point, because they're related by some dimension-full parameter that I called R, and that one I haven't actually specified. So if you go in the literature and find people trying to be very ambitious and find a model for Schwarzschild black holes, for Kerr black holes, and the sort, what I would always ask would be, okay, have they right and left temperatures, but also are they sort of proportional to my physical temperatures or not? But they could still differ perhaps in the CFT temperatures, because that would correspond then to having specified the scale R in a different way. And that's sort of a lower level of disagreement. But it seems to me that all the proposals I'm aware of, these are all, you know, proposals that are not particularly well motivated, but they tend to have the same ratio of left and right physical temperatures that I do. I should answer, which is sort of the partial answer to Saab's question, which was the, look, you look at a formula, you squint and you say, well, there's clearly two pieces here. Well, okay, what's the algorithm? Well, the algorithm I'm proposing is actually that if you give me a black hole that I'm not, you know, privy to the details of, but you say, okay, I'm not going to show you the entropy formula. How should I put it into left and right form? I'm going to instruct you to compute not just the area of the horizon the way you normally do, you should compute also the area of the inner horizon. I know fully well that the inner horizon is unstable, but it nevertheless has a well-defined area that satisfies many nice properties, actually. You know, the actual value is not thermodynamic in the sense, but I don't mean to interpret it in that way. But if you compute that, I'm telling you that you should compute the left minus right entropies by computing the area of the inner horizon. This gives you an algorithm then for computing S left plus S right, which is the usual algorithm, compute the area divided by 4g. Now I also told you how to compute the difference of the two. Then you can figure out yourself how to compute S left and S right independently. But this is an algorithm that I'm proposing would work in all sorts of cases, including those that I haven't yet actually constructed. So I say, okay, this is the algorithm. How am I proposing you test such an algorithm? Well, once I have proposed my CFT split in some unambiguous way into left movers and right movers, the CFT does have a universal property which is level matching. Sort of L0 minus L0 bar has to be an integer. That translates in this geometrical language to the feature that a plus and a minus has to be an integer if you multiply the two. It is a fact that if you take the Kerr entropy formula for the outer area, I showed it to you, now go compute it for the inner area. Actually, it looks the same as a formula with some m squared, but instead of plus square root, it gives minus the square root. So therefore, my algorithm for unambiguously splitting into two pieces is indeed that you sort of look at the inner area to decide what the difference is between the two sides. But now I'm saying multiply the two areas. Well, then you get the m squared term squared, so I'm m fourth kind of term. And then minus the square root term, which also is being squared. Then the m to the fourth actually are canceling out. And you end with j squared. And that's what I've written in a precise formula here, that a plus times a minus is a square of an integer. This is the one thing that I actually know from general principles is quantized, even in the Kerr black hole. The angular momentum is quantized. And I get here really something with coefficient 1. So I expected that the CFT should be quantized in some kind of way, especially the level matching, because I don't know the dynamics of this thing, but that's just a kinematical constraint. If there really is a dual CFT, I should expect this kind of thing. Since it is there, I'm encouraged that my phenomenological analysis might in fact be on the right track, even though you might, of course, still say that this is absolutely unpersuasive. Yeah?
There was a paper recently by Matt Visser who looked at charged black holes, charged rotating black holes, I think. He said that this doesn't come out to be an integer anymore.
That I am not aware of, because I've checked the charged black holes.
Well, it was something to do with the choice of units for measuring the charge, I think. He was claiming that factors of the fine structure constant were entered on the right-hand side.
That's very interesting, and I really, that I should definitely follow up on, and I don't believe it. Not aware, because I've looked at so many examples. In fact, I've looked, for example, black rings for this. You know, I asked Roberto Emperon for something where they hadn't even written the metric down. It was only in his Mathematica code. And I said, could you please compute the inner area for this one?
I think his claim was that people are always computing the charge in geometric units, and assuming it's integer quantized in those units, but if you use the correct units, then you get factors of the fine structure constant.
Okay, well, this is possible, but I believe I can show the quantization for these charges actually using just the Dirac quantization of electric and magnetic duals. So I don't really need the independent quantizations. I only need the products. But maybe I'm embedding it in an incorrect way. So that's very interesting. Well, maybe I'll be shown wrong. But nevertheless, I'll take this to be encouraging. So this was the Kerr part. I went very slowly. So I want to move on and look at the more standard, black holes that people often look at in string theory. They're more complicated. That's why I didn't start with them right away, because the notation gets a bit more complicated. So what I have in mind now is to take some of these highly charged black holes, 4 charged black holes in n equal 4, n equal 8 supergravity. So they have mass and angular momentum, but now also a variety of charges, 4 charges in fact. And now you have to introduce, in order to be able to write anything, parametric charges. So it gets more complicated. I trade my capital M, the physical mass, for little m, j for my angular momentum parameter, little a, but these are just parametric angular momentum and masses, and then for each of the charges I have these boost angles here. So this is sort of complicated. In fact, in order to even keep these formulae more or less manageable, I introduced these abbreviations here for the product of all the coshas of these angles. And all this you don't have to memorize, you just have to remember that, well, there are a bunch of charges, 4 of them. They will appear through the boost angles. You can think about it that way. There's a mass, there's angular momentum. They will appear through the M and A, but the actual map is a bit more complicated and is written there. So how does the entropy work now? Well, again, the entropy formula, remarkably actually, sort of looks a little bit like before. There's some term without a square root plus a term with a square root. And these are generalized versions, of course, of what of what one had in the Kerr case. Here I've written the left and right separately using this rule of the inner area. Now, I'm still encouraged for two reasons that this can work with my phenomenological model. One is that the dependence on the angular momentum here can still be accounted for by this physical assumption that only right movers have the ability to carry angular momentum, but the left movers do not. And the angular momentum only appear on this side, which means that if we had a CFT model that accounted for the non-rotating black hole, we would automatically get a CFT model that accounted for the rotating black hole as well, if we just modeled the angular momentum as an R charge. And that then I would take as encouragement that we're on the right track. Another encouragement would be that if I go and check that my level matching condition, my generalized level matching condition is satisfied, that roughly requires that I take the square of this minus the square of this. The square of this is easy, that just means I get rid of the square root. And then I take the two expressions subtracted. Now this is complicated because it depends on all these m's and pi's and coshes and sinches and all that sort of stuff. It depends on the angular momentum in a simple way, just the way we had before, but all the other stuff appears in a complicated way. Except it turns out to not be that complicated. These pi c's here were actually coshes. These pi s's here were cinches. When you multiply the coshes and cinches, they give sinh of 2 times the boost angle, and that just happens to be the physical charge. So when I square this, all the cosh squares will subtract off from the cosh squares down here. The sinh squares will subtract off with the sinh squares that come from down there, but the cross term, cosh times sinh, will stay. And that is exactly the physical charge Q, for which I actually know something about the quantization condition. And the quantization condition is that what I get here is exactly the J4 invariant of the either n equal 4 or n equal 8 theory that I get. In other words, pretty much the only really nice integer that there is in the system is what I get. It was clear at some level that I should have gotten that, because you would know maybe in the extremal limit where a plus and a minus become equal, area should just give the square root of J4. But what I'm saying is that even when we are totally off extremality, we have a nice integer lurking in the system. And I think we should pay attention, because this is what you would have expected if there was a level matching condition. Since this is true, I'm thinking maybe there is indeed a level matching condition. In this case, we get an actual expression for the central charge density again. And now we are in a context that's so large where I really have 4 charges, angular momentum, mass. This is a family that's big enough that I can actually go to limits where I really understand what I'm doing, such as a near supersymmetric limit. This would amount to taking 3 of my 4 charges to be very big, such that I get very near the extremal limit. Mass is going to be very near the BPS limit. If I go to that limit, my formula actually simplifies, because my coshes and cinches become very similar. Coshes and cinches are very similar when the deltas are very big, and therefore in that limit, these formula here that reduces, and it reduces actually to exactly the standard formula, where this, as I say, looks like something cubed. Well, the something cubed really is exactly the standard sort of product of 3 charges, which I can interpret in a more geometrical framework as the triple intersection of a bunch of phi branes that are wrapping some force cycle inside a Calabi-Yau. And in this sense, this formula actually reduces in the supersymmetric limit or near supersymmetric limit to something that I know is true. So the family I'm having here, you can think about as an extrapolation of extremality, far from extremality, of something that we actually understand, which is sort of the MSW model, and hoping or guessing that it works all the way off. So that's a good time for question on philosophy.
Can I just ask a question about your formula for the product of the left and the right areas?
Yes.
I mean, this is for asymptotically flat. It has to be asymptotically flat,
Yes.
because otherwise it's dimensional parameter.
That's right. Yeah, that's asymptotically flat, that's right. No, you're right. There's some generalization that's been proposed for some of the other contexts, and it's sort of more complicated, but there still seems to be an integer lurking in there. It just lurks in there in a more complicated way. So Gibbons and Svedich and somebody else, possibly Pope, has a formula that they,
Which 5D black holes does it apply to?
these are, standard n equal 4, n equal 8, 4 charge type black holes. But the is what I'm having in mind for this thing here. But as I say, the area quantization, for example, also works for the for these for the black rings.
For any black ring.
Well, certainly.
If I just take a vacuum black.
Let me say the vacuum black rings that I can find. Yes. Yes. Right. Yes. Yes. It works for that. Mm-hmm.
And if you don't have an inner horizon, so if you just have a single.
No, there are two. There are two. What?
What happens if you don't have?
Oh, sorry. When you don't have an inner horizon, you're right. That I treat as a singular limit. Where no, that's right. That's right. Where that sort of gives zero. So then it's an indefinite formula.
So
That's right. So you need some charge. You need some charge to resolve it.
We don't have a charge with the Pomeranski Senko. So
Right.
it's kind of tied up with the existence of a regular extreme or limit.
I think that's right. That's right. But we checked it for sort of these 9-parameter rings or whatever that were the most general rings that Roberta could tell me existed, that he knew of. And then, yeah, I think recently there was a paper actually by Castro and somebody else that wrote up some of those things. But, So let me try to now actually show you a little bit of geometries. It's so I'm not going to go into all the terrible details that could be involved here, but you know, I want a bit to show you that I've done real work, not just philosophy. So well, this is the explicit geometry with all the charges turned on. Here we have some potential A that we think about as the potential for rotation, because these are generally rotating black holes. So this is the A1 form that's, you know, going around in the azimuthal direction. I've written it, this black hole in a form that's not quite the standard way. Maybe we would write the curved black hole in that I've had then here just some sort of three-dimensional space. It's not a flat base, but anyway, this is the base space that I need. And it's parametrized in terms of these functions x and g. They have other names in the Kerr literature, but since those names had already been used for something else, then I've used brand new names, x and g. I think normally they're called delta and something else. But anyway, these are standard functions that do appear when you write down the Kerr formula. But then, because we have all these charges, this is a much more complicated geometry. All the complications, they appear mostly through this function delta here, that appears sort of as a conformal factor in front of the base space, and then it's the inverse conformal factor in front of the time part. This delta here is the one that has all the complications, or at least most of the complications. There are a few complications that sits in the rotation part here, that the angles and this charges and such come in a kind of complicated way. So to understand this metric, one has to somehow digest some of all this stuff. So one of the pieces of evidence that is inspiring me is that if you go beyond the entropy formula, to give this dual 2D CFT, but we can make some more precise observations by instead trying to probe our geometry. Like, for example, looking at the scalar wave equation, the Laplacian basically, in the background of this geometry is a little bit of a complicated geometry, so you have to work a little bit to invert the metric and reorganize it in a way that looks nice. Once you do that, what you find is that the general Laplacian, it looks like this. Still fits on one line, but in part it's because I'm cheating, of course, that these deltas and a's are quite complicated functions of all the parametric charges and masses and angular momentum. So what am I looking for in this geometry? Well, one of the things I'm looking for is that I recall that Kerr black holes allow separation of variables. Now it turns out that when we add all these charges, it becomes a much, much more complicated system, but it still has separation of variables. Basically, we still have a radial equation that sits here, and we have an angular equation that sits here, and then there's this funny thing here. As I told, there was this A that was a bit complicated, and there was a delta that was tremendously complicated. But if you take this combination here, you will find that in fact they factorize out a G, which itself is some function of r and theta, and the whole thing becomes a function that depends on r plus a function that depends on theta. And what that means is that this entire equation actually separates nicely into something that's radially dependent plus something that's angular dependent. Therefore, I have separation of variables. So even though I add all my charges, I still have separation of variables. It's one of the features that I don't really know what to do about, but it does at least facilitate my analysis, that I have this sort of nice technical feature. But it's not just that that leads me to want to look at the wave equation, because this resulting radial equation is actually a quite nice radial equation. Now that we no longer have, behavior in the full angular direction, we can just look at the radial behavior. And it's a very nice one. It has two singularities. The singularities are where x here is 0, which actually is at the two horizons, and the poles at those horizons of this equation is exactly the temperatures multiplied by 2 pi and stuff like that. But basically these are the inverse temperatures, the indices at these two regular horizons. So therefore the equation has nice sort of polynomial behavior at two nice places, and you can patch these things together. There's a third singularity, which is at infinity. So at r going to infinity, there's also some behavior that can be analyzed using a polynomial, but it's not as nice. It's actually what is called an irregular singularity, and it's because my delta, which was this overall conformal factor, is asymptoting to r to the fourth, which is what it takes for me to get asymptotically flat space. So because I'm insisting on asymptotically flat space, I've also encountered a problem, which is that my equation is a bit harder to solve and analyze properly because I have this singularity at infinity. If only I had been a bit luckier, like this delta here, for example, was of order r squared or something like that, or slower, then the singularity at infinity would also be regular. And in that case, my equation would reduce down to a hypergeometric equation, which famously is just a character of SL2. And if I were to find an SL2 symmetry that permuted these three singularities, I would declare victory, because it's a well-known theorem that if you have an SL2, you also have a Virasoro. Just kidding. But at least if you don't have an SL2, you certainly don't have a Virasoro. So you would feel that you're on the right way. So therefore, this is sort of what we're looking for, is that it seems like whatever we're looking for is very close to something where we actually get. In fact, if this delta here was, even stronger, not proportional to r squared, proportional to r, then the angular Laplacian would in fact even become just really the spherical Laplacian, and that would indicate that I would have an unbroken symmetry. And also, it is true that if I analyze these things as I would normally in ADS, I would find conformal weights at infinity that would give just the angular momentum conformal weights, and that would be something that I like a lot because it reminds me of life back in ADS3, even though in this case I don't have an ADS3 at all. So I really would like if it had been just that delta was a bit different than the actual delta that I have. But I guess I'm just dreaming. So let's try to think, what is the physical obstacle of this delta that seems to be in the way towards me discovering an SL2 symmetry? Well, in some cases I could say, well, actually that delta is well approximated near the black hole. Far away from the black hole, it was this r to the fourth that made me go off to flat space, but near the black hole, I could try to approximate that delta and then turn it into one of these deltas that I kind of liked, so that I discover an SL2. And you can think about it as saying that that's exactly what people would normally do when we go and analyze near extremal black holes. One way to think about it is that in the wave equation, we are comparing this term here, which is the near horizon term. The x goes to 0 at the horizon, so it's something that blows up near the horizon. And then there's this term here that did separate variables, but it was rising a bit too quickly at infinity. But near the horizon, this term is really not all that important anyway, because this term here blows up after all. So this term always is subdominant near the horizon. So maybe this asymptotic behavior sitting in the delta is not so important after all. And certainly this is exactly true in cases where we have decoupling limits, formal decoupling limits, like near extremal, near horizon symmetries, both in near extremal Kerr, in near supersymmetric situations. I can understand that as saying that this term here is big near the horizon, this term is big at infinity, and I can find an intermediate region where neither of them are big, and therefore I can actually decouple the two complications, the infinity complication from the near horizon complication. So that reminds me of what it is I would like. Of course, in general, these two terms are just of the same order, because in general, I don't have any parameters that I'm tuning, and if I know parameters that I'm tuning, these two terms are well of the same order. Nevertheless, it was popular, and the reason I started to revisit this problem a couple of years ago was this paper by Strominger and his collaborators that simply said, well, look, let's just ignore these terms we don't like, these terms whose role in life it is to get asymptotically flat boundary conditions for the black holes. Let's just ignore them in the wave equation. Then in the wave equation, we now really do have an SL2. In fact, not just a single SL2, we have an SL2 squared. And SL2 being a non-abelian group, I know how to normalize now my generators of the SL2. So in particular, I can discover what L naught is and L naught bar. Of course, I could write formula also for L plus minus 1 and L plus minus 1 bar. I just haven't. But L1 and L1, L0 and L0 bar are very nice ones. They're basically translation generators along the sort of T phi directions. But we knew already, of course, that there were two killing directions, the T direction and the phi direction, but we didn't know perhaps what natural basis there would be, which linear combinations of the T's and phi's should you take, and also how should you normalize these things. Now, in this setup, we do know how to normalize them. And indeed, we have one side that knows about the angular momentum, and then we have the other side that doesn't know about the angular momentum, and we have normalization for both of these things. So we can sort of say that we have these CFT type coordinates, T plus, that really now has gotten a length involved with them. In fact, we can determine what the temperatures are for these things because phi here has period 2 pi. So that way we can determine just by comparing this with a standard thermal CFT where, you know, it's 4 pi squared over T is the periodicity of a high temperature system. And this way we actually find the CFT temperatures. And that was one of the things that we a priori didn't know. In the system, in my phenomenological analysis, I didn't really know what the CFT temperature should be. I knew what the physical temperature should be, but there was an overall factor that differed from the physical temperatures to the CFT temperatures, so I hadn't actually determined much in my phenomenological analysis, but here I get an extra piece because I've normalized generators near SL2. The CFT temperatures determined in this manner are nice in that they really are proportional to the ones I proposed for the physical temperatures already. And the proportionality factor, given by some formula that's not particularly illuminating, especially since these symbols were defined incredibly quickly, if at all. But whatever, there's some formula, very concrete formula in terms of all the different parametric charges and such. And now that I know that size, I can go and look at my charge, at my formula for the central charge density. And since I know the size now of the circle, I can find my central charge. And if I believe this was the correct determination of R, what I get is 12J. That 12J is very intriguing because it's the formula that previously was determined in a much more concrete and well-argued way as the correct central charge for Kerr CFT that can be argued to be the correct central charge for Kerr CFT at extremality and near extremality. But what this determination is indicating is that maybe the same central charge can be used all the way off extremality. At least one can find evidence, one can find a remnant of that central charge all the way off. Yeah?
So this analysis is for the scalar wave equation, right?
Yes.
The linear horizon.
Absolutely.
So what about the other modes, like vectors or tensors?
They will satisfy the same thing, and I'll show you. That's right. That's right. But this, at any rate, is intriguing, and there was one of the things that, this was the result that Strominger and Castro and Maloney found, and it was what sort of intrigued me to say, well, we want to look a little bit at this again. But indeed, there's some questions. One of the ones was the ones that came up. Obviously, there were the, well, this was based on the ignoring the terms that we didn't like. That's something that might work in your social life, but it will not usually work in physics, to just sort of ignoring the stuff you don't like. The reasoning was limited just to the scalar wave equation. You might say, well, look, was that really needed, that step? I mean, is this geometrical or what is it? And besides, this SL2, I mean, I'm saying that it has a central charge and whatnot, but well, is it a Virasor? That would be a good first step. And these are some of the questions that one could raise. And well, there are other questions one could raise, but these are some questions that at least I have made some progress on. So these are the ones that I'll focus on. So first, let me take a detour to try to analyze just the thermodynamics of these black holes. They were, after all, kind of complicated. You may recall that this was the actual full metric. I wrote it a little bit differently now because at first go, I had the T sitting over all the way to the left and then a spatial base, but I really haven't rewritten it, other than that I've reordered my terms in that I've decided that I would like my R phi plane to be together and my theta T to be together. So I've rewritten it just by reordering my four terms. in the equation. And this I've done for a reason that you'll see shortly, is because it's more illuminating for the purpose of thermodynamics. So this x function here, I really had an actual x in my solution, but let me just imagine that it is some function of r. It is in my actual solution, but that's what I'm going to keep x kind of general now, while I analyze this metric here, just to try to understand getting my bearing, because the actual functions are so complicated that I might as well keeping them general. My g here was pretty much the same as x, but it had a different theta dependence. So therefore, I will make x arbitrary, and then say g has a slight theta dependence, and I'm going to put that in. And this a that somehow had to do with the rotation, this delta had to do with this overall conformal thingy, those I would just keep arbitrary for now, because frankly they were so complicated and disgusting that I really hope that I will never going to need them anyway. Now what can I do in this general setting, where I haven't frankly even specified what theory I'm in? I've just specified a quite general black hole. It's almost the most general metric I could imagine. Not quite, but it's up there. Well, I could find the ergosphere, for example. The ergosphere I find by basically determining where's my static limit. And this I determine, of course, then by just looking at the coefficient in front of GTT here, it's g equal to 0. And then I determine that g owing to 0 is my ergosphere, it's the position of my ergosphere. Maybe there's several, whatever, I haven't specified what g is, but this is where I'd have static limits. Also, I could discover where is my event horizon. That's where the GT here might change signature at the point where g changes signature, but in the whole T phi plane, I have to find a determinant, which is really multiplying this times that, and that means that it's x that ends up being the thing that flips sign whenever I have an event horizon, or horizon. It's not strictly an event horizon in all cases, but that's at x equals 0. So that's nice that I can give you equations like this without actually having specified totally my black hole. I can actually proceed and look at not just causal structure, but look at the entire thermodynamics, finding the rotational velocity, finding the temperature, the Hawking temperature, finding the entropy, computing the area, stuff like that. The remarkable thing is that I can do all this without actually having totally specified my black hole. I can write the results for each of these things here in terms exclusively of this A potential that was sort of the potential for rotation. I have assumed in the process here that this A phi potential for rotation has an explicit sort of dependence on angle, on theta like this, and then an undetermined R dependence. And that I have assumed because that is what I need in order for this rotation velocity, in fact, to be constant along the horizon. So whatever theory I'm in, it better be true that A would have this general form. So this is very interesting formulae, and this is a different way of putting thermodynamics than normally. Notice here that even for non-rotating black holes, I'm using this A potential in a very essential way. I'm describing the non-rotating black holes as a limit of the rotating black holes. And in that limit, my potential for rotation is proportional, of course, to just the rotational parameter, and then somehow the slope as I go to 0 is what seems to be the defining feature for being able to describe, formulae of this form. They're all sort of determined in terms of my rotational potential. And these abstract expressions, they give the correct thermodynamics for the explicit solutions, and trust me, they're much, much easier to use than actually having to find things like the rotational velocity in directly using this quite complicated geometry. Yeah?
Are you using any, are you assuming any properties for x?
No, it's a function of R. Look, I'm not being very rigorous. I always have in mind that the function of x is going to end up, look, it's a quadratic polynomial in the actual solutions, but, if it's not a quadratic polynomial, it might have other numbers of poles and stuff like that. So I haven't really, so there'd be a number of other horizons and stuff. So I haven't fully, looked at the causal structure all the way in. If this was a very complicated function, surely the causal structure could be incredibly complicated. I'm mostly interested in the outer horizon after all. So, I haven't done a totally good job. The reason I'm showing you this, though, is because of a striking feature. The striking feature is that the causal structure of this general set of black holes and of thermodynamics, they were computed with minimal assumptions and they do not depend on the conformal factor delta. The rotational velocity, the temperature, the entire area of the black hole, all of these things I can compute for this general black hole without having even specified delta. Delta is an arbitrary function of r and theta with some minimal positivity and things like that, because there's some square roots. But it's basically an entirely independent function. What does this mean? The way I interpret this is that delta is a feature of the embedding into the ambient space-time. It's not something that has to do with the black hole itself. The black hole itself, all its temperature, its entropy, its causal structure, is all something that is encoded in these other functions, x and g and a, but delta I'm interpreting as the function that tells the black hole in what environment it finds itself in. Delta had to take a particular form in order for this black hole to attach on to flat space at infinity, but I could contemplate other deltas that would correspond to the black hole not attaching on to flat space, and I would say that if I contemplated such other deltas, my thinking would be that that would be like putting the very same black hole gently, without having in any way changed it, because I haven't changed any of its thermodynamics, to sort of put it in a box and contemplate changing the boundary conditions at infinity using some kind of infrared regulator. That would mean that I maintain my thermodynamics of the black hole space-time, but I'm going to instead put them in a different environment. So the proposal is to simply change delta from what it actually was. Because as I explained, I really didn't like the actual delta. It didn't give me an SL2. So if I instead chose a different delta, then I'd be all set. Which delta should I choose? Well, I would like to maintain separability of the scalar wave equation, and I would like it to be some reasonably nice function of r, Bayesian analytical function, a polynomial in r. And with those things, those assumptions, technical assumptions, I managed to find an explicit delta. This is uniquely determined, and this is the alternate delta that is still very complicated. You can't really digest it just by looking at it, but it's different because at large r, it has a much milder behavior, which is linear in r and for large r, unlike the original delta that went to r to the fourth. But this particular delta is the one that is determined just by me wanting separability and wanting it to be not being still a nice function of r.
I'm sorry, can you remind me what was the r squared behavior instead?
That was a matter of whether I wanted the sphere to be flat, or the sphere to be spherical. Sorry, the angular directions to truly be spherical, or whether I allow it to be oblate. And here I did not. But the technical result now, which actually is in part responds then to the question of, am I limited to the wave equation? No, I'm not. The technical result is that the metric I've written down for you, that you haven't absorbed, but in terms of g and x and a and delta, if I were to change the delta from the very complicated formula I had earlier to this delta, this is the geometry whose exact wave equation has the SL2. It's the geometry whose exact wave equation is a hypergeometric function.
But this metric doesn't solve anything then, presumably.
Not a priori. Now we'll get to that. We'll get to that. That's right. So now once you answer some questions, you get other questions. But this does answer the question, though, that if I take this geometry now and put another wave equation in it, not the scalar wave equation, but instead put the Dirac equation, or put the vector equation in it, this will still have the SL2R. This is now a geometrical feature. So once you've gotten it in the geometry, you made a little bit of progress, because you're not limited to the scalar wave equation. So you answer, in some ways, some of the questions. Is that instead of being sort of doing analysis that is purely at the level of the wave equation, now there's analysis at the level of the geometry. To say that now you can take many attitudes. You could of course say that, well, maybe I could think about this delta being a good approximation for the actual delta. And to the extent these two are good approximations of each other, this would be a more conventional changing the geometry from what it actually is to something that's very similar. But well, it's a good approximation, and that's okay. Yeah.
Can you say what aspect of the geometry, What structure in this geometry exists that guarantees this hypergeometric?
Come again? What structure?
So is there something like a killing tensor or some object defined in this space-time?
I am not sure. I've been trying to look for a killing tensor.
Presumably it's not a killing tensor because you had one of them before and it didn't work.
Yes, that's right. But I've been trying to, yes, I had a killing tensor before, that's right. And I still have a killing tensor. But what feature is, I do not know. I mean, I don't know. I know that I have these SL2 type generators that commutes with the killing tensor, but I only have a very low tech description of that. I mean, sort of very coordinate dependent, very, not quite right. No,
So-
not, yeah.
Does it generate new kind of zeros?
Does it what?
New kind of zeros of delta? I mean, does it?
But I don't care about the zeros of delta. I don't care about the zeros of delta. You know, it's, I mean, but this one, yeah, it probably is positive definite or something like that. Yes, I don't know. But it's, I'm not particularly interested in the zero, you know, it was the zeros of G that gave me the, you know, and X that gave me the causal structure. So this is where, this is, you know, I mean, I imagine that if this was crazy enough, I could screw it up because, as I say, this does appear with some square roots and stuff like that, and sometimes that's probably bad. And clearly I'm assuming that it's not bad in order for it to factorize out. But it's more just like, if this was 0, yeah, well, then I might multiply by 0 and divide by 0. But it still seems somehow, if it's regular, it factors out. If it's regular,
So what's the new asymptotic geometry?
so the new asymptotic geometry, it's that I'm not sure I've written down, but it's an asymptotically conical geometry. It's it looks pretty nice. So it looks a little Lifshitz type like, but it has not been analyzed properly. You know, I've done a half, you know, a moderate job, but clearly one can do a much better job. Yeah.
We would get the same type of scaling even with R squared. I mean, different critical exponent with R squared.
Yeah,
the
that's
same
right.
story.
Yeah, that's right.
You said that this function delta, we should really think of it as some function that determines the embedding of the
Yes.
black hole itself into some different ambient space. But surely the thermodynamics of black holes in a asymptotically flat space is very different from the thermodynamics in, say, a black hole in a box.
Yeah, but you could see though that on these formulae, these actual formulae, I think what I've done, and it's true that there probably some formal work there that needs to be thought better through, but is that I maintain my definition of time from my original flat space time. Because I'm saying that was, after all, you know, part of what I think really was part of the actual black hole in order for me to get temperature and other things like that's sort of meaningful. But other than that, I'm cutting off. And it seems that I can only do this in a unique way. That you know, as long as I have these technical things like separability maintained, then, but yes, surely it's very different. Surely it's very different, absolutely. In particular, this near horizon type region, which is now put into a box. A box that's a nice box, a nice smooth box. Not just a crude box, but a nice box that is such that it creates an SL2. That was sort of almost there in the near horizon region, but now it's exactly there. Yeah.
Is it possible that the new asymptotic geometry is conformal to ADS2 cross S2?
It's not. It's not. It's not. No. It's not.
If you look at massless probe fields, right?
Yeah, it's not. But yeah, that too, almost. In fact, yeah, no, it's not. But it's that I can, maybe I think I will show you that shortly. I think what it is, at least a little bit about it, because there's a nice way to think about it, what the geometry is. Then you can work your way back. One question there was that came up was that, well, look, now that I took the rules to be that delta can be whatever it wants, then I've changed the geometry, and once I changed the geometry, indeed, the Einstein equations would not be satisfied in general. My interpretation of that actually is, at the first level of defense, is that frankly I don't really care, because boxes, once you put things in a box, have to be made of something. And that something is something extraneous to the system I'm analyzing, and therefore I don't really have to normally care. Normally when you put something in a box that has Dirichlet conditions or something, nobody's hassling you of saying, what exactly do you make the box from? But since I know that you would be hassling, and I wasn't after all also worried, I did try to figure out, could one perhaps actually figure out what matter there is? And well, in some situations one can argue that this additional matter is actually very mild, in fact, more or less, you know, non-existent, and that not much matter is needed. That's these cases where we're near extremality. That corresponds to the box sort of being self-creating. But in general, I can show that the matter is very sensible. It satisfies all the nice energy conditions. And in fact, there's a simple realization of what matter it is that you need to support these solutions. So you really can put them on shell. What it requires is that you mess up the couplings that you originally had between your scalar fields and your vector fields. You have to deform these couplings, but into a theory that still is perfectly sensible, and that I think I can describe in just one word, actually, shortly.
Sorry, I got confused. So there's a new physical scale with your box.
There's a new
There's
physical
a
scale.
associated with this box. Where's the scale of this box?
The scale of this box, I don't think, is there a scale?
In what sense is it a box?
It's a box in that anything that has finite energy near the horizon region can no longer escape to infinity. Basically, GTT becomes big at infinity, like in ADS. Not in the same way, but it becomes big. Once that becomes big, it means that anything with finite energy will get redshifted infinitely much, therefore cannot escape to infinity. It will get bounced back, anything with finite energy in the near horizon region. So that way you say, okay, stuff that is near the black hole really belongs to the black hole. Stuff, however, that originally was very far away does not belong to the black hole.
Perhaps you answered this when you mentioned the point about time being preserved
Yes.
in these new boundary conditions.
Mhm.
One of the reasons why asymptotic flatness is relevant is that that's where the Hawking temperature is
Yeah.
defined, because you don't have, if it's not asymptotically flat, how do you, there's no
You're right.
meaning to the definition.
I
mean, there's no, it's it's an arbitrary scale.
well, it's not that arbitrary, because there still is, after all, the T parameter, which is, it has this imaginary periodicity and stuff like that, and it's, I would say that is the thing that I'm not messing around with.
No, but you can change the periodicity by changing the coordinates, unless you have it fixed in.
No, of course, I could rescale and then use a new T, and then, but that I think that from a CFT point of view is not an absolute, that just means I rescale everything in my theory. If I rescale everything in my theory, I rescale nothing. Right? I mean, it's so I think that's safe enough. But yeah, look,
it's a scaling of T, so you have to have T has to be defined.
Look,
It has to be defined. Usually, it's defined at infinity in a standard way.
yeah, and look,
You don't have that.
I wish I could
But
give you a better and more powerful response to that, but it's well, I've told you the mechanical procedure. Try to keep the same. Try to look. What geometry is it that has the nice near horizon wave equations and other stuff, and the same thermodynamics and whatever? Instead of doing it just at the level of the wave equation, what geometry is it? And that, I think, is progress. But does it itself raise new questions? Yep, it does.
If you added curvature corrections, would the thermodynamics still be independent of the conformal?
I think so, because I don't think I specified what theory I was in. I said, this is the geometry. I didn't say what theory it solved. I said, suppose this geometry solves some theory. What rotational velocity does it have, blah, 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 these things. That was the question I answered. So I don't think I care what theory it was a solution to. I have an example of a theory that's sensible and nice, and for which it is a solution. And that, of course, makes me feel like, okay, so far so good. Because it could have been that it was totally crazy. But could it be a solution to other theories? Yes. And higher curvature, sure, that would just change the precise relation between various parameters. I don't think that would be. Yeah. One way to think about this 4D geometry, which I've written for you in a way, because I've written this complicated thing with some delta, and I've told you what the delta was. But I'm telling you, it's kind of hard to analyze. A good way to analyze it, the best I've found, was to take the 4D geometry and actually make it a slice of a 5D geometry. So introduce an extra auxiliary coordinate, alpha, that I don't think about as particularly physical. But I'm saying that I will describe my 4D space-time as a slice in this 5D space-time that has an extra kk coordinate. Why do I do that? Well, because if I do that and choose my B field here appropriately, then I can cancel various offending terms inside the geometry that seem to somehow mix in awkward ways the angular directions and the RT directions in such a way that I get something that's manifestly factorized. This is the T, R, and then this new alpha coordinate. This is a three-dimensional space. Times some sphere. I've written it with primes here because it's not really spheres that were written in terms of the actual, it's not really the sphere, but it's something that's made out of only theta and phi. That means that in this geometry here, if I were to write down the wave equation, for example, it's obviously manifest that this here, that you get a wave equation for this part and a wave equation for that part. And in particular, if I then say, oh, I'm only interested in waves that don't depend on alpha, I'm in good shape. So therefore, I will, in this form here, I can see separability and such features in a manifest way. And I can analyze various properties. In fact, there was one thing that I hadn't mentioned, which was that early on I claimed that the wave equation was separable. Well, actually, almost. It was separable up to an overall kind of complicated conformal factor, the delta, which is such that the Laplacian was separable, but only if the input equal to 0. If you wanted to look at the massive Laplacian, you would have to multiply the mass by some complicated delta, and that delta was such that actually it would mess up the full separability. In the massive case, you only have massless separation. So what you should do instead is to look at couplings to scalars that are not minimally coupled, that instead are minimally coupled to this 5D metric, which corresponds to conformally coupled to the 4D metric, and those ones are separable even in the massive case. So that sort of ties up one loose end. But another loose end is that this 5D representation, it really has a Virasoro, because it is locally ADS3 cross S2. So I've embedded my actual 4D spacetime as a slice into this 5D spacetime, and this 5D spacetime does have a Virasoro. Now, deformations of the 4D spacetime are those that are independent of the alpha. So although I have found a Virasoro, I have not found a Virasoro that acts on my 4D excitations as a full Virasoro. It only acts on this extra coordinate, which somehow I had in mind should be an auxiliary coordinate. In order to get a full Virasoro, really, that's physical, I should elevate that alpha to be an actual physical coordinate. It sort of would be the physical coordinate along my actual physical CFT. Except that CFT, unlike in Kerr, which sort of lives along the azimuthal angle in the actual 4D spacetime, in this case, it lives along some auxiliary fifth direction. And therefore, I'm both conceptually and also technically, not entirely there where I want it to be. Although it's very encouraging that you find a Virasoro that's entering the game, even though it doesn't seem to quite act on the quantities that I have in the game in the manner that I'd hoped for. So this is the summary. I just got the leave now sign. What I've actually done is that I've been pursuing, this conformal symmetry for general black holes is something that has been mumbled about for years, and I think that we have certainly not established it, but I think there are a few technical things here. I think this reorganization of the black hole thermodynamics in a way that gets this independence of this sort of conformal factor. It's not exactly a conformal factor. The thing I call delta is conformal in front of the spatial and then inverse in front of the time. So that factor somehow is not important. That is, for thermodynamics, I think is significant. I also think that it's nice that we have a geometric interpretation of the part of the geometry that has this SL2 symmetry. It's a geometric interpretation, geometric construction. So it's done in space-time as opposed to being done at the level of the wave equation, which at least is a technical piece of progress. And then we have these rudiments of a full Virasoro algebra. And it is something that does identify some of the parameters of the Virasoro, even for these very general black holes. I haven't, simplified the black holes. I maintained the full general black holes, and then I mucked around with the space-time. And then maybe you'll say, well, look, you cheated. Now it's a different space-time. Well, true. But it seems to me to be at least clarifying some of the procedures that people have been proposing for these things. Thanks for your attention.
Questions? Yeah.
So it's known that there are black holes which are different, but nevertheless they've got the same near horizon geometry. And it would seem that in your description they would be described with the same microscopic CFT.
I didn't understand. So there are some black holes that
there
have...
are black holes which are different black holes,
Yes.
which have the same near horizon geometry. And therefore, in your picture,
What are you referring to? I don't know, but
for example, you have the under-rotating KK black hole has the same near horizon geometry as double spinning minus Perry, and they are different black holes, but nevertheless they have the same near horizon geometry.
yeah, some part of their near horizon geometry is the same. I do think in my picture I might cut off actually further out than the comparison you're talking about. The comparison you're talking about, I think, is inside the ergosphere, right?
Well, yeah, it's strictly speaking.
Right, but I'm maintaining even the causal structure, so I'm cutting off actually a bit further out. So I think in this picture, I do think I could distinguish this particular example. But in principle, there could be examples, yes, that would say, no, I'm going to say they're the same thing. And yeah, that's true. I mean, look, if you have black holes here, you know, they're not isolated quantum systems, they're, you know, engaging with the world at large, far away. And clearly, if you want a theory of the black hole by itself, you somehow have to, I mean, that's going to be part of the rules, is that you have to somehow say that, no, I only out to here is part of this quantum system. And that's, you know, if at all, you know, you think that there is such a thing as a microscopic description of a Schwarzschild black hole, this is going to be part of what you have to answer, proposing parts of an answer. Yeah?
Apparently, what is the intuition that you had used to say that there is a two-dimensional CFT that is hiding behind this black hole?
Intuition is the entropy formula. It's look, it splits nicely into two pieces, and it's proportional to T, and you know, so therefore it seems that yeah, each of these two entropies is proportional to T. So that's the intuition. You know, is that, you know, and the fact that even before you've done anything, the wave equation is so close, all but in only one term, that doesn't seem somehow important. It seems like it only matters far away. That prevents it from being an SL2 squared, but basically being an SL2 hypergeometric equation, right? So that makes you think that Virasoro would be nice. Now, I mean, is it compelling? I don't know. I've been trying to present you the evidence, right? But you know, you could interpret it differently. Say, well, look, you're making too much out of a few things that are admittedly facts, but I would have a very hard time to try to put it into a three-dimensional CFT, because I don't see anything similar to that. Right? Yeah.
Do you think this separability this is an important feature of your analysis? Is it? So
Yeah.
if you didn't separate, you wouldn't see these SL2s.
I think that's right. That's right.
If you considered a scalar field with a nonlinear potential,
Yeah, I considered a lot about the separability, but I have not. I've worn down one student, and now I'm going at a postdoc
so in what cases
to try to understand properly. Look, it's so technical. I can, you know, find equivalence between this statement and that statement, whatever. But I don't know what the separability somehow seems important. I mean, say for Kerr, I don't know what it really means. I mean, I understand. Yes, there's a killing tensor, there's a Miliano tensor. There's I hear it, and there are various equivalence between these various statements, but I don't really know what it. Is that significant? Or are these just sort of mathematical niceties?
So in what cases have you seen this SL2 for? You mentioned the scalar field, free scalar field, and you've also done the Dirac equation.
Yes, I haven't done it, but it has to be there because
Massive Dirac equation.
the massive I have not checked. I don't know. I don't know how to do. But I know that the massless Dirac equation, it follows
but the
from.
massless, you have this Tucholsky equation.
Yes.
And so, yeah, I believe that. But in the massive case, does it?
Yeah, no, I agree that that's not automatic. That's not automatic. But I believe that once I have found an SL2 in the geometry, then I'm ensured that will act on perturbations of arbitrary spin.
You haven't found that yet.
You know, it's well, no, I mean, I showed it to you. I mean, in this ADS, basically in this higher dimensional representation, you know, that means that I can reduce down. I can write, you know, so I can make designer coupling such that I really do have all the nice things. But yeah, I mean, we'd like to work out a few more details.
Okay, let's thank the speaker again.